Will we have access to these videos in the future?
Yes, they're on Moodle right now.
I mean, like, just future.
Oh yes, so they're also hosted on YouTube. So
So just search you up on YouTube?
yeah, just search my name, it'll come up. If not, yeah. I don't say any of that in there but if you want to, that way you can always go back and find them again. So there's a lot of them. So there's one because ISU is encouraging all teachers to have their own YouTube channel because it's linked to your ISU account anyway. That way they can upload all their individual videos and stuff like that. So, okay, any questions about? One other term that we'll get going here. But any questions with open, closed, or open and short circuits, anything like that? Okay. So we have one thing to remember: if we have a closed circuit, we have a continuous current path to get us from positive to negative of our voltage supply. So this is a complete network. We've got connections. From a positive voltage to ground, or the negative voltage, whatever it may be.
What's the difference between ground and negative voltage?
Generally, ground is a common point that we're going to use, or if we talk about like a negative voltage, it's like the negative pin on the voltage terminal. A lot of the times those are used as the same. Sometimes they're different depending on where we want our reference point to be. Because when you add in a ground, then you can change how things actually behave, as far as how you measure them, how you look at them, that kind of stuff. Okay, the next one is that we're going to talk about is electrical shock. You guys should remember that from the safety videos. What's an electrical shock? It's when you get shocked. Yeah, current passing through your body. So it's the physical sensation resulting from current passing through the body. So in the case of tasers, yes, you do have a higher voltage that's locking up your muscles and that kind of stuff. The current is what can kill you. Okay. Not usually, because for one, it's pulsing and it's not there that long, but it's enough to override your body's natural electrical impulses and actually and takes control for a split second.
It's just basically overriding your program.
Oh yeah.
Yeah.
Yes. Yes, they are. Okay, so one of the things next we're going to talk about is precision. Precision is repeatability. How many times can I do something to get the same number, to get the same answer? Also, it's if you're doing the same thing over and over and over again, you should be getting the same value. Who knows what the definition of insanity is? Expecting a different result. If you understand that you're going to get the same result, that's not necessarily insanity. Okay? But precision is repeatability. Can you do this over and over and over again and get the same value? Okay? Whether or not it's correct, that's a different story. Remember with the target, precision is how well are things grouped together. The repeatability. Accuracy is your range of error from being correct. So accuracy is how close do you get to the right answer? How close do you get to that bullseye? Precision is how many times can you do that? So just like we were talking about before with targets and shooting and that kind of stuff, if you can hit the same spot every single time, you're very precise. If you hit in the same spot, but not in the center of the bullseye, you're not very accurate. Okay? There's also times when you could be clustered all the way around the bullseye, but you're not consistently hitting the same spot. You're accurate, but you're not precise. So there is differences, and then there's times and places when you need those. Sometimes, if your precision is good, this just takes a little bit of nudging, a little bit of pushing you into the right direction. Maybe you're not quite using values. Maybe you're using the nominal value for the resistor when you should be using the measured value for your resistor. That's one of the differences too, like in lab. And that's why I'm harping on this a lot, especially early on. Use your measured values for your resistors, capacitors, that kind of stuff when you do your calculations. Because not only one, your precision is going to increase by just the repetition of doing those tasks, but your accuracy between what you calculate and what you measure, you're going to see them almost line up. Till we get to AC. Then there's some things outside of your control that we're not taking into account for AC. But that's just the nature of it.
So if we're using a resistor like the 1 or 2 that was in our lab,
Mm-hmm.
the testing it wasn't very accurate, should we just use the labeled?
Yes, yeah. If you can't get a very good accurate number, you can use kind of the average of the values that you get. Once you get outside of those values, everything should lock in pretty close.
Yeah. Everything after that.
Yeah. A lot of times we're not going to have you do a circuit that uses a 0.67 ohm resistor. There may be stuff that you design that you need that, but if you're down that precise, you're close enough for all intents and purposes in this class.
So are there like, just out of curiosity, are there like a set of like just more standard resistors than others, or?
Yes, we do have some values out there for in the 5% and the 10% range. I think there's a copy of that on my desk, but you can look them up. If you just typed in standard resistor values, it'll give you the whole list. And usually we'll have those in stock. One of the things I like to say is this joke I've heard a little bit between precision and accuracy and that kind of stuff. So the idea is two guys go to a bar. There's an engineer and a mathematician. They both start taking bets on who can get to the bottle of beer at the end of the counter fastest. But the rules they say is you can only move half the distance from where you're at to the beer. Well, eventually, looking at it, the mathematician just gives up and says, well, that's stupid. You'll never get there. The engineer takes 5 steps and says, that's close enough, and grabs it. So it's a definition between precision and accuracy. You can be as accurate as you want as the mathematician and, dividing by half every single time. You're right. You're never going to get there. But at some point, your objective is here. You're right here. That's close enough. For all intents and purposes, you're within your rate of tolerance. And in our case, it's going to be 5%. So just keep those in mind. The last one we want to cover is error. So kind of pulling in from this definition again. Error. This is the difference between the true or best guess or best accepted value and the measured value. So again, that's what you guys are testing. How far off are they? Okay, that's where our plus and minus 10% come into. Because we're saying we are going to accept an error of 10% of that nominal value, and it's going to be good. In industry, like I was saying with some of the quality controls that we had, if it was within our threshold, if it was in a range, it was considered good. A lot of the times those, depending on what the products were, and like I said with those, you may have some that operate at, 90% peak efficiency. You can sell those for a lot more money because they're very precise than you can for the ones that are not as precise, or maybe not nearly as precise. You'll find that when you get into the transistors next semester. They're rated for a certain beta, but the range is from, I think it's 100 to 350. And it is a huge swing. The difference between a 100 and a 300 it's exponential. So, but you can get those devices for 15 cents versus the high precision ones that are like 150 to 175. Those cost $4 or $5 a piece. So things to consider when you're building stuff. What is my error of my devices? Okay. Do I have a device in there that could be within its tolerance, but then inside of its tolerance could throw me outside of my tolerance? So I always have to be aware of those factors that can come into play. Any questions about some of the terminology we're going to use? Okay, I'm sure there'll be more as they come up. Don't be hesitant to ask for an explanation if I use a term that you guys are not familiar with. These are just kind of some of the basics to get you guys understanding these. All right, let's shift gear from terminology and let's get into some of the math. Now, one of the reasons we go through fractions, and we actually spend quite a lot of time dealing with fractions, because anything that we do in electronics is going to result in some sort of a fraction. You figure resistance is equal to voltage divided by current. Before we even get started, we have a fraction. So fractions are everywhere in math. And once we learn how we can manipulate these fractions a little bit, we can start to recognize patterns. We can see things. When you get into calculus, it's really easy to use these rules because now all of a sudden you can swap things in and out and simplify your problem from this huge mess of equations and shove it down into something that's very, very manageable and very easy to solve. And that's kind of the whole idea behind this, is we want to increase everything or decrease everything to their simplest point to be able to solve for it. When we simplify these things down, it's less stuff to punch into our calculators. When it's less stuff to punch into our calculators, it's not as much error that we can introduce into our equations. Because sometimes you just fat finger the 6 when you meant to hit a 3. And, if it's in a decimal, that 6 is probably not that big of a deal. But if you fat finger a 6 instead of a 3 when it's an exponent, now you're going to end up on completely opposite ends of the spectrum. Okay, so when we're multiplying fractions, we're going to multiply them together to get different values. And one way we can look at these and how these are going to carry through. So we have 3/7. We're going to multiply that by 4/5. So when we do this, what are we going to multiply together? What are we going to divide together? Well, for starters, we want to keep things on the same level. If they're a numerator, we want to keep it as a numerator. If it's a denominator, we want to keep it as the denominator. So we can combine these guys together. So this is now 3 times 4 over 7 times 5. Okay? Now that we have this in this form, we have terms that are multiplied over dividing. We can even split those up if we wanted to. If for some reason this made it easier, we could rearrange the values. So this ends up being, what's 3 times 4? 12, and 7 times 5? 35. So instead of trying to, type in these calculators, 3 over 7 times 4 over 5, we could just look at it as 2 simple multiplication problems. Obviously, I expect you guys to have some of your times tables memorized. I'm not going to go through and quiz you. I mean, we could. I can give you little gold stars or stickers or whatever if you give me your 3 times tables. If you need that, then we could do that. But if not, like I said, this is what we've got the calculators for. Bring yours to class. Make sure you have them because we're going to have these types of problems all the time. Let's see. And you can rearrange these too as needed. So you can split these numbers up a little bit and change it. So let's look at a different one. Let's say we had 3/7 multiplied by 4/15. Okay. We do the same thing. We've got 3/4. We've got 7 times 15. We also could look at this and we could rearrange these guys since it's all multiplication and division. We could have 3/15 by 4/7 because we haven't changed the equation at all. We've just reordered it. This guy would simplify right off the bat. And now we've created a much easier problem just by looking at it and kind of rearranging and applying the mathematical rules that we already have. Or we could simplify it at the end, but this is, just to visually look at it, when we're multiplying and dividing, we can rearrange what they're multiplying together as long as we don't break up parentheses, we don't break up exponents, things like that. Questions about that? So dividing fractions. This is going to happen a lot too. We have one number that's the dividend, and the number that's called the divisor. Do you guys remember which one's which? Yep. Dividend's on top, the divisor on top. Basically, the whole group is the dividend. The divisor is how many groups we're trying to split it into. One way to think about it. So the rules for this, when we're dividing with fractions, is division easy? Not necessarily. Multiplication is easier. Okay? So if we have 5/9 divided by 25/18, that's kind of a lot. There's a lot of things to be plugged into our calculator. So what do we have in our toolbox to be able to make this problem easier to solve? We're going to convert it into a multiplication problem. Okay? So what we do is we take the divisor, we invert it, and we multiply it to the dividend. So this becomes 5/9 times 18/25. Okay, another way we can, as we're doing this, we can simplify them. We don't necessarily have to draw these out in 3 times 4 times whatever. We have our 7 times 15. We can also look through and we can cross multiply. Okay, if we have numbers on top, on the numerator and the denominator that will go into each other, we can cancel them out. So when we look at this, we've got a 5 and a 25. Do those go into each other? Yeah. So this is going to reduce to a 1. This is going to reduce to a 5. We have 9 and 18. Again, it's going to go 1 and 2. So doing what we just did on the second one, but just using cross multiplication. And again, we're using multiplication to help solve our division problem. Because that's all a fraction is. It's just a division. So we end up with 2/5. The reason we bring this up is because we're going to be doing formulas that are going to have lots of these parts, where we end up with a fraction on top, we end up with fractions on bottom. Remember, you can invert and multiply and to create it into a multiplication problem, which then will usually have something that starts to fall away. Whether it be a number, whether it be units, that kind of stuff as well. Questions about that? Okay? What is a prime number? 7. And why is 7 a prime number? Yep, can be divided by 1 in itself. So what are some common prime numbers that we're going to see? 1, 2, 3, 5, 7, 13, things like that. I'm not expecting you to understand and know all of them, but really start recognizing the basics of them. What about 10? Is 10 a prime number? How about 144? What about 121? Nope. So some of these we kind of intuitive. If you have a question about it, you can always try and divide it. I think there's some calculators that has a tool in it that will tell you if it's a prime number, and it'll automatically do the calculations and things like that. That's probably on the 89s and some of the more scientific ones, but always give it a shot. See what you can break it up into first. So prime factors, basically what we want to look at is we want to break numbers down into their prime factors. Because once we get them down, that's as small as they can go. Once they're there, then we can start canceling things out because we're going to be looking at prime numbers compared to, or the primes of one number compared to the primes of another number. We're going to use it for different ways to factor and calculate it. So what we want to do is we want to separate, we want to factor the number 616 into its prime numbers. So there's multiple ways we can go about doing this, but one thing we just kind of start with is, well, we start with 616. What's a prime number that we can take out of it immediately? 2. So we split this guy up. We get 2 and 308. Now this guy's prime, we're good there, but the 308's not, so we're going to continually break this guy down. So now we can break this 308 down again. Let's break it up into, let's just say 4. Will 4 go into 308? Goes in 77 times. And the reason I picked 4 is because it quickly separates it into another prime. 4 then becomes 2 and 2. Yep. So now we've taken this number and we've reduced it just to a series of prime numbers. So now we have 2 times 2 times 2 times 7 times 11. Now, why do you guys think we would need to do something like that? Well, one of the things is when we're looking for common multiples, when we're trying to add and subtract fractions based on when they have different bases. This is a way that we can get there. This is also, like I said, for a common multiple, as we need to find out, we're trying to convert this into an equivalent value, and we want to compare things at the same rate. This will get us there, because then we can just compare the prime numbers to find out what value we need to get to. Because then it'll, like I said, it'll get into a lot of being able to reduce our equations very, very quickly when we can start to break these up into the fractions. Like, oh, this is going to come out, this is going to come out. It'll save us a little bit on the math, especially when you don't have a calculator or you don't have a scientific calculator at that time. Because there's been times I've been doing these problems. I don't have my calculator on me, so I have to use my phone. My phone doesn't like to handle a lot of the big numbers and the big digits that we multiply and divide by. Breaking it down to the prime factors, it's a lot easier to do that than the other one. But the biggest thing is we're understanding we can break apart these big complex numbers into smaller values. When we get into some simultaneous equations, these are going to come important again. Okay, so for our next example, let's factor 4,058. And I don't care how you factor them, how you keep track of them. I like using this genealogical breakdown of it, this hierarchical method. Either way you want to do it, doesn't matter to me. This is just how I do it, just keep track of everything. I'll give you guys a couple minutes to look at this one. And then the idea too is we want to break things down to where they're prime, because then we know we can't reduce them any further. What are we coming up with prime factors for this guy? It is a difficult one. Anybody have an answer? Yep, that's it. Yes. The idea behind this is, yes, you can go through that and work it through it. I have run this out before. I've developed a couple programs, things like that, things I found online, and 2029 is a prime number. Okay. The reason you want to break it down is because when we get here in this next section or two, we're going to be using these to solve, like I said, for the least common multiples. How can I combine all, a series of numbers together? What's the common multiple? What's the least common multiple? Because then we can also brute force it, but then we might have to do a little bit more reducing to it later. So, any questions? Yes. Because it was fun. Just to show you that the prime numbers can be thousands of value. Okay. Just because you hear prime does not mean it's gonna come down to a 2, 3, 5, or 7. We could have a prime number that's in the 2,000 range, and that's perfectly acceptable. All right. So the idea behind prime factorization is, what can I do? What can I take out of this number to be able to reduce it farther? Okay. So when we're reducing fractions, we want to take out the same value of the top and of the bottom. So to start simple, okay, I have 2/4. What does that reduce down to? 1/2. Okay. The other way we can look at it, if this wasn't quite nearly as obvious, is we break it up into its prime factors. Okay. We have 2. We have 2 times 2. So when we have a value on the top and the value on the bottom, they're going to cancel. And so by reducing it, we end up with 1/2. So by taking numbers that seem very large and factoring them out, we can then, instead of trying to guess, if I take 5 out of each side, what's going to end up with? If I take 6 out of each side, what am I going to end up with? And going on with that, you can factor these numbers down and get a value that is very, very quick and breaks down what we can and can't take away. So for more difficulty, (99/165). What's that going to reduce down to? Again, we can start breaking it up into its prime factors. So 99 breaks up into what? 11 times 9. That can break up even farther to 11 times 3 times 3. Okay? 165 breaks up into what? 5, 3, and 11. So right off the bat, the 11s are going to fall off, and a 3 is going to fall off, because we have both one on top and bottom. And so we end up with 3/5. So there's one way that we can speed it up. Because like you guys were saying in some of the looks I was getting, you want me to do what? You want me to factor this value, reduce it down? And we quickly did it just by breaking it up into its individual prime factors without having to do a lot of guesswork. And that's one of the things we're trying to do, is trying to eliminate the guesswork. Any questions? We're good there? Really what it comes down to is finding out what can I remove from both the top, the numerator, and the denominator at the same time. Because if you remove it, remember you're basically changing it by a factor of 1, which is not changing your original equation. That's another thing you're going to be doing in calculus a lot, and later on in the semesters we're going to be changing these equations. We're going to be putting in equivalencies. What can I put in to make this easier to solve where I'm not going to actually change the formula? That's where we get into like going with the special formulas for power, resistance, current, and voltage. When you start mixing in, if you have resistance and current, how do you find power? That type of a thing. If you don't have the voltage. If you have the current and resistance, you can find it. Same way here, is we're just making substitutions that are equal. Okay, the next method we're going to talk about is finding the least common multiple. Anybody know what the least common multiple is? Right? The least common multiple, put simply, is what is the multiple, what number does a series of numbers go into that's the smallest. So the idea being is we can find a multiple of any series of values. And we can either do it through this one or we can brute force it. A lot of times when you brute force it, you're going to get an astrologically large number. Okay? When you have that big of a number, then it starts getting into rounding issues. Well, if you round it off here, it's going to change your value. If you round it off in another spot, it's going to change it, and vice versa. Using the least common multiple, we can pinpoint what's the smallest value that we can use that will still accurately represent this number. Because there's times, like I said, we want to compare things that are of the same magnitude. If you're looking at numbers, you want to be able to have a number of, milli compared to micro or to mega. You got a -3 versus a 6. You want to convert them into one or the other, so that way you can look at them both in the same terms. Again, comparing them apples to apples, and then specifically comparing them to the same types of apples. So in this case, what we're going to do is we're going to factor out the values. Then we're going to use those factors to help us solve what's the least common multiple of these guys. So what we have is we have 16, 99, and 104. We want to find what is the least common multiple that 16, 99, and 104 go into. Yeah, go ahead and start looking into your primes, breaking these up into your prime numbers. So I'll tell you right now, if we were just to take these numbers and brute force them, the least common, or the multiple that we would get with these guys, that's not the least common multiple. That's if we were to brute force it. That's simply taking 16 times 99 times 104, which is a large number because there's more things going on. There's a lot more values to consider. The one we're looking at is a lot smaller than that. So the first step we want to do is we want to start breaking these guys up into their individual factorizations. So 99 we already factored. What did we say that was? 3 times 3 times 11. So that's the start. Okay, 16 splits up into what? Yep. Because you get 16 by multiplying 4 by 4. And then each of those 4 splits up into the 2 2s. Okay, 104. What do we start splitting that guy up into? 13 and So 3 2s. Okay, so now that we have these broken up, here's how we're going to use them. Like I said, once we reduce them down into the prime factors, this thing starts to get easy. We're going to start going through and looking at just the primes. What do I need in my answer? And it has to match those primes. So for the first number, I have to have the value of 16. So my least common multiple has to contain 4 2s. It has to. So we put those into our equation. That takes care of each of them. Now we come down and look at our next value, is 99. So for our multiple to be divisible by 99, it has to have 2 3s and an 11 in it. So we just simply add in 2 3s and an 11. Now we look at the last value. To have 104, we need these factors in it. So when we look, we need 3 2s and a 13. We have 3 2s already. We don't have to add them in there. The 13, we do. So we add that into our value. Then once we have everything calculated as far as what we need, we multiply all those values together. That will give us our least common multiple. Which, what does that number come out to be? Now, let's double check. We take the 20592, we divide that by 16. That gives us 1,287. So a big number, but it's a whole number. We take the 20592, we divide that by 99, we get 208. We take the 20592, we divide that by 104, we get 198. So this is the smallest number that all 3 of these values will go into. And the reason we look into that is because this is how we're going to start multiplying, or it's how we're going to start adding and subtracting fractions. Because to add and subtract in fractions, they have to be in the same denominator. And this is how we can quickly get there. Instead of just trying to, plug in a bunch of numbers and calculate it, just factor them out. We're going to start to get to values where we have, get into there on this one, or is that next week? Where we're going to have values we're going to be having values like that. Just so you guys are aware, that's a Z. My Z's and my 2's look way too similar, so I put a line through my Z's and I put a line through my 7's. Just so I can see what I'm different. So that way, if you guys have questions of what I'm writing, that's what they are. But the same reason here, we have denominators that have different values. We would go through the exact same process, factor these guys out, create it, our least common multiple, and then that way we know what do we have to multiply this by to get to this value. This is why we're doing that, so we can start getting into where we have variables included in their fractions. Okay, let's try something. Let's try another one. Any questions? Okay, so I want the lowest common multiple of 2, 4, and 9. Okay? So we're going to break this up. We got 2, 4, and 9. What is the answer if we just brute force it? So if we take 2 times 4 times 9, that's guaranteed to give us a multiple. Equals 72. Yeah, let's just not do that. So we know our value at most is going to be 72. Okay, but we're trying to find the least common multiple. So 2 breaks up into 2 and 1. We just leave it alone as a 2. The 4 breaks up into 2 and 2. The 9 breaks up into 3 and 3. The least common multiple, we need a 2 and a 1. So we'll just put the 2 in there. We're just going to drop the 1. Anytime you're multiplying 1, you can really drop it in, drop it off as needed. It's there and it's not at the same time. It's like Schrodinger's cat. Anybody not know what Schrodinger's cat was? You've heard of it? Basically, it was a hypothesis given that there was a cat inside of a box, or at least we were told there was a cat inside their box. That cat both exists and not exists at the same time until you open that box and look in there. So somebody could say there's a cat in there, but until you look in there, you don't know, and it's still, both the possibilities have equal chances of being true, so they're both saying to occur at the same time. So we got 2. Okay, we need to add in the 4, so what do we need there? Did I break somebody in the back? There's your philosophy lesson for the semester. So for the 2, we need 1 2. For the 4, we need 2 2s, so we add in the second one. For the 9, we need 2 3s. That number becomes 36. And the reason also, like I said, that we want to find the least common multiples is because this is already reducing this fraction for when we come up later. Because remember, as we go on, we're going to be multiplying this by 72. We're going to be multiplying other things by 72. The numbers are going to get larger and larger and larger, and then we have to reduce them. This is taking the reduction steps already as we go to make it easier for us as we go day to day. These techniques, like I said, we're going to be using them a lot throughout all the electronics that we do. Not necessarily finding the least common multiple, but understanding that we can use that to simplify our answers as we go, instead of having to simplify them at the very end. This is all leading into the adding and subtracting of fractions, because that's what we're going to be doing a lot of the time. When we get into using Kirchhoff's voltage law and Kirchhoff's current law, we're going to be adding and subtracting voltages. So if you think about it, so using Kirchhoff's voltage law, it's the voltage total is equal to the voltage drop of component 1 plus the voltage drop of 2 plus the voltage drop of 3, so on and so forth, for however many components you have. Well, in this case, what is voltage? How do we solve for voltage? Actually, this is kind of a bad example, but either way, we can break these up into the smaller ones. So IR1 plus I2, R2, so on and so forth. Currents. When we're dealing with a total current with the branches, it's going to be equal to the voltage divided by the resistance. These are going to start to change, so this is another way where we can quickly add and subtract these guys and get them into common denominators. Just kind of as examples of how we would use these things in the real life. Okay, any questions about solving the least common multiples? Okay, as far as we have quiz-wise, where's my mouse? There is a section in here for reducing fractions to the least common terms, to lowest terms, adding and subtracting fractions, which we're going to get to tomorrow, and then adding and subtracting and converting fractions into and out of mixed numbers. Mixed numbers and improper fractions, going back and forth. Because there's going to be times where you want them as mixed numbers. There's going to be times when you want them as improper fractions. So going back and forth. that's the math section for this week. So the last section we'll cover tomorrow, and then we will start getting into the theory of series circuits and voltmeters. So with that, anybody have any questions before we end? No? Okay. Have a good night, guys. Yes.